So here's our lesson. We got to talk about two things. One, we got to talk about how do we use electricity, and the other one is how do we make it? Because, like I said before I started recording here, electricity isn't free. It doesn't just show up somewhere. You have to pay. Now, I mean, take your cell phones for example. When your cell phone dies, you have to plug it back into the wall socket and recharge it. Now, if you do that at school, the school pays the power bill, right? If you do it at home, then your parents are paying the power bill. But like somebody has to pay the power bill for you to recharge your phone. It's not free. Does that make sense? So we got to talk about where does the electricity come from? How do we make it? What can we do with it? Because electricity really has transformed our lives. And I have just kind of a generic picture I found online. I mean, just look at some of the devices we've got here. From cars to ovens to refrigerators to televisions to computers to flashlights and lamps. 100 years ago, this stuff didn't exist. Right? I mean, not that it was like the dark ages, but it was definitely the pre-technology ages. Right? So I think you guys get the point I'm trying to make here. So I'm going to give you a bit of a history lesson here. This is one of the single most important discoveries, probably in science. I mean, I don't know that I could rank them. Maybe the discovery of penicillin would be pretty high up there. Some of Einstein's discoveries are high, but this one's got to be like top 5, top 10. So here's the story. It's 1831. A guy named Michael Faraday. He's playing around with a magnet and a coil of wire. And what he was trying to do actually was trying to induce some sort of voltage to create a Wi-Fi signal. He didn't call it a Wi-Fi signal at the time, but he was actually trying to create basically a prehistoric radio or a prehistoric like transmitter of some kind. That's what he was trying to do. And by accident, he kind of discovered this concept. It's called electromagnetic induction. And I'm going to show you guys this tomorrow in the lab. Here's basically the idea. He took a piece of coiled wire and he moved a magnet inside of it. And when he moved a magnet inside of it and he attached a galvanometer, the galvanometer needle moved. Do you guys remember what a galvanometer measures from yesterday? Courtney? Yeah, and amps is current. Current is like the measure of how many electrons are flowing. And so what ended up happening is by merely moving a magnet inside a coil of wire, you actually create electricity. Hence the term electromagnetic induction. What ends up happening is electricity is induced. You create electricity by moving a magnet with a coil of wire. And this one discovery, through about 190 or so, 180 years of innovation, has actually allowed us to now create our own electricity. Because prior to this, we didn't have electricity. Okay. So basically, the idea is take the magnet, move it into the coil of wire, and it actually causes electricity to occur. Okay. I've got kind of a picture here, kind of showing the concept here. If you take a magnet and move it inside a coil of wire, this little amperage device here, it moved, meaning that current flows. Now here's the problem though. Once you take the magnet and put it inside the coil of wire and leave it there, nothing happens. This only occurs when you move the magnet in, current flows. But once the magnet is just sitting inside the coil of wire, it stops again, which kind of sucks. Because you can make a little bit of electricity temporarily, but only when you move the device. So that means you always have to be in motion. Does that make sense? Now, what he also discovered, though, is that if he pulls the magnet back out again, though, it actually causes the current to flow the opposite way. So at least motion could cause electricity. We actually had a name for that sort of energy. You guys remember the name we gave to energy that's involved with motion? Mechanical, yeah. If you have mechanical energy, he discovered that mechanical energy could form electricity. And you guys have probably seen pictures or like videos, like in modern media. The typical idea would be like a hamster wheel, and like the hamster's running on the wheel, and as the wheel spins around in a circle, it creates electricity. Ever seen like some sort of device like that where someone's like running or moving something around in a circle? The problem is you have to have that mechanical energy. Well, eventually, some engineers were quite bright. They figured out how to make a generator, because really that's what a generator does, is it takes motion and converts it to electricity. And I've got a couple of different models of them. I'll show you them later when I'm closer in person, because I can't show you guys this one all at the same time. But this is basically a very basic generator. And what ends up happening is you've got this little, I know it's far away, but you've got these like spun little coils of wire right here. Right here. Can you guys see that? And what's supposed to happen is that if you spin this, if you manually spin it around, and you put some magnets through these slots right here, I don't have them there, but put some magnets through those slots, it'll actually cause electricity to form. And I've got a way better picture here at the front, though. So let me see if I can try to explain what happens. Okay. What you do is you take a coil of wire. So you have your wire, it coils around like this. Okay. And then you put it inside a magnetic field. So like one side of a magnet's here, one side's right here. If you spin that wire around, it'll actually cause electricity to run through the circuit, which is super cool. And like one of the most important innovations of all time. But the problem is you have to physically spin the little like coil of wire around. Does that make sense? So you could stand there all day and basically crank some sort of device and you'd make electricity. Anybody ever actually seen a device like that? Like I've seen crank radios before, where you have to just like crank a little thing like that and it creates enough electricity to run a radio. Or flashlights. There's some flashlights where you just like you have to do some sort of like spinning or turning of something and it'll create electricity. That'll work too. Yeah, you've seen some of these then. Okay. So it's that exact same principle. Yeah. So here's the idea then. The faster you turn the wire, the more electricity you make. So if I spin the thing this fast, there's not a lot of current. But if I spin it really fast, I make a lot of current. Well, once people discovered that this is a cool way to make electricity, that's awesome, but who wants to stand there all day and keep cranking some sort of thing around in circles over and over again? That's not efficient. So what physicists and scientists discovered is we need to use nature to do it for us. And in southern Alberta, you guys probably know this, maybe you don't know all the details, but we have a lot of these windmills. So what a windmill does then is it does the spinning. Okay? Effectively, a windmill is this device right here. Okay? Inside the windmill is some sort of device that's going to spin around in circles like this. But rather than me spinning it, the wind pushes, it's called a turbine. You guys ever heard that word before, turbine? It pushes the turbine around in circles. It causes this thing to spin, and if this wire spins inside of some magnets, I'll put some magnets there later, it actually causes electricity. And so we can generate our own power using that. Now there's three main sources of electricity where we would use a turbine. One is wind power. We have lots of that in southern Alberta. The other two I've got listed here. This one is hydroelectric power. Does anybody know how hydroelectric power works? Yeah, I mean, basically you have to make a dam, though. You guys know what a dam is? Not a swear word, but like a dam with just one M. Yeah, dam. Right there. That's a dam. The way a dam works is you build up a whole bunch of water by building a wall on the end of a river. And then what you do is you let a little bit of water go through. You don't let all of the water go through, but a little bit of water gets to spill through these sections right here. And when it does that, as the water goes through, it causes some sort of thing to spin. Again, if you can spin a coil of wire and a magnet next to each other, that's what Faraday discovered way back in 1931 can create electricity. So that's one way. The other main natural source of power we have is tidal power. When you're at, anybody ever been to Nova Scotia before? You've seen the Bay of Fundy, how it goes like up and down with the tides? It's really incredible. As the tides go up and down, you can actually use them to spin these turbines around as well. Exact same principle. So spin a coil of wire inside some magnets, you can make electricity. And I want to show you this tomorrow because when I say it in words, I don't think it's quite as applicable as when I actually show you. So I'll try to show you guys this tomorrow. But this was revolutionary. Okay. 1831, Faraday. I'm going to talk about it for the rest of the unit. Because really, this changes everything. Now that we can generate our own electricity, we can do something with it, right? And the things that we can do with it are pretty cool. Here's a picture of a dam, by the way, the hydroelectric dam. What you do is you build a big wall in front of the water supply. Right? So this is a river or something, a lake. You dam it off, and then a little bit of water is allowed to go through. As that water goes through, it causes this turbine, I have it listed right here, this turbine to spin. So the water is kind of going through here. It makes the turbine spin. The turbine causes the generator to spin. Well, the generator has inside of it a coil of wire, inside some magnets. Hence the term electricity, magnetic, from magnets, induction. You're making electricity from electricity and magnets. Okay. Now, one of the ways that we've actually managed to find a way to harness this power is through the use of batteries. And I actually like to show you how that same sort of principle applies in a battery. Now, the chemical word for battery is actually called a cell, kind of like the word jail cell, only a cell. Okay. Actually like to make a temporary battery right now, but I want to show you this picture first. Here's how a battery more or less functions. What you need to have is a couple of pieces of metal here and here, and we call those electrodes. Okay, these are called electrodes. And what happens is electrons are going to go from one electrode through a wire and over to the other electrode. And what ends up happening is it has to have a complete circuit, though. Remember how electrons have to go all the way through a circuit? Once they go from here to here, they actually have to go back again through this little bridge, and they make a full loop. Now, I don't have quite the setup right here, but I'm actually going to make a temporary battery with the stuff I have up here, and we're going to run the clock. So, you're right, it is already running, but that's because I'm cheating. It's already running because there's one of these. So now that I take this battery out, it's not running. So here's how this works. In order to make an electrochemical cell, you need to have, how can I arrange this so you guys can see this better? So what I'm going to have here is some different pieces of metal. I need to actually, to make this work, I'm going to make 3 batteries because one battery is not strong enough. So I've got here some copper and I've got some zinc. These are known as your electrodes. These are basically your coppers. These are your zincs right here. And I'm going to take one of each and I'm going to put them inside these cells here. So I'm going to put copper, copper, copper in here. And then inside these little cups right here, I'm going to put the zinc. Okay. Now, I'm going to start to connect up some wires here. And the way this works is I need to connect them in like a set here. So you have to give me a second to try this. I've got to go from this guy to this one. Then I need to go from this one to this one. Then if I got this right, this one should now be, let's see, it's going to go from zinc. This one actually, I need to change the order up here. Gotta go backwards. This one I'm going to use red. Red is supposed to be the hot wire. So this is where the electrons are going to run through. And I'm going to attach to the back of the clock here. Hopefully I get it right. And then this last one's going to run from here and attach to the other back side of the clock. Okay, now the clock isn't running though, is it? The reason why is I don't have a full circuit. Because although the electrons can run through this wire, and I have all these wires hooked up to metals, I actually have to have a liquid solution down there as well. That's called an electrolyte. These are called electrodes. Stuff down here is called an electrolyte. And I'm just going to make a basic solution using a couple of chemicals. One's called copper sulfate, one's called zinc sulfate. So you have to give me a second. I forgot to bring a scoopula. I was silly. 1 second. Okay, so what I'm going to do is I'm going to take some zinc sulfate and I'm going to put it into some of these containers here. Okay. And then I'm going to add some water to each of these little cups. Now, to try to explain what's happening, see how there's 2 different beakers right here? To save space, what's actually happening here is that there are 2 beakers. Here are the 2 beakers next to each other, but to save space, we literally put one of them inside the other one. That's kind of what's happening here. So these 2 beakers, rather than them being side by side, beaker next to beaker with an electrode in each, I'm actually going to put them inside each other. It saves space. I'm going to add some water to this guy. And stir it up. Add some water to this guy. And stir. And some water to this one. And stir. Okay, so that's one of my solutions. I have to make another solution though. So that's the solution that's inside like just this little cup right here. So it's not running yet though, is it? No. Okay, so now I need to make a solution inside the big beakers. Now this stuff here, it's actually got a nice blue color to it. Yeah. So, blue crystals. Yeah, they're like bath salts almost. But they're not bath salts. Now, last time I did this, I actually set it up before class, so I'm taking a bit of a risk here because I hope this eventually works. So I'm going to stir this one all up. And we'll stir this guy all up. And we'll stir this guy up. And then, the question is whether I have these on the right ones here. Okay. It's not working yet. I might have to play with this until I get it to work. Copper goes to zinc, zinc goes to copper. Copper's going to lose electrons. Yeah. No, that's not right. Sorry, I just need a data booklet. I need to remind myself how this works. How do I not have a single data booklet sitting here? What do you need? I'm looking for my chemistry data booklet. I can't remember which way this works now. I want to make it work. Copper's going to go to copper solid and gain electrons. So if copper's going to gain electrons, zinc's going to lose electrons. So this zinc is losing electrons. Thank you. Are you looking for me? Yeah, when you have time. Okay, you might have to come back in a little while though. Oh, okay. Yeah, come find me in a little while here. Not working yet. Okay, I'm gonna make this work. Okay, I don't want to take all day to make it work. I took a risk. Rather than making it before class, I thought I'd make it in class. So I will make this work. Okay. Did any of you guys see it working actually with the previous class I made it with? Somebody see that? Okay, so I will get it to work, but I'll do it later. Okay. Anyways, let me keep moving here. We're gonna make that clock work eventually. Here's basically the concept of what's happening. Okay, if you can kind of picture the idea, what's supposed to happen is one of those electrodes is going to lose some electrons. And electrons are going to flow through the wire. They're going to flow through a device. Do you know what we call a device in an electrical circuit? We have a name for it. That's called a load. It's going to flow through a load. In our example right here, the load is supposed to be the clock. But what should happen is electrons should go from one of these guys right here, go through the clock, and then show up at the other electrode. So what should happen here, since I get it to work, is electrons should be going like from this guy right here, through here, through here, through here, through the clock, and then come back through the other side. You guys see that? I'm going to do it one more time. Electrons are going to go from here, through here, through here, through here, through the clock, and back out the other side. And if it's done properly, it should be a full circuit. The problem I have here is that somewhere along the way, I don't have a full circuit. And that's why the clock's not moving. So I'm gonna have to play with it later when I get more time. But in lieu of that, so here's the words I need you guys to know. The words are electrolyte and electrodes. Those are the two parts of a battery. You guys with me? I know I kind of had to run around and do some stuff. Give me focus again, okay? Two parts of a battery. Two parts of a battery are an electrolyte and an electrode. Okay? The electrodes are the pieces of metal. Okay? Like this piece of metal right here and this piece of metal right here. Those are called electrodes. Okay? Ideally, the electrons should flow from one to the other. But you have to have a full just need the electrodes, you also need the electrolyte, which is like the liquid. Because what it's supposed to do is it's supposed to keep the circuit going. You guys can see how there's a picture right here of an arrow saying anion flow. Electrons are supposed to flow from here to here, and then anions are supposed to keep the circuit going. If anywhere along the way, is it working? Stop. Well, rather than there being a bridge, the way we do is we put one beaker inside the other one, and that kind of solves the problem. So like this one right here shows them next to each other. What I could do though is literally take like this beaker and put it like inside of that beaker just to save space. That's kind of what's happening in that example right there. Okay, the other thing I need you guys to know in terms of terminology is the two parts of the battery. You guys have probably seen this before. All batteries are labeled with a positive side and a negative side. Yeah. So the side that gains electrons is called a cathode. This is the positive side of your battery. And the anode is the negative side of your battery. Now, all batteries are set up a little bit differently. The battery that I took out of here actually has that same stuff. It's just the way it works is that you guys have seen one of these batteries before, right? There's like this there's like a metal core that goes right through the middle. That's actually one of the two parts here. This little metal piece that kind of protrudes through, it's actually the positive electrode. The negative electrode is actually the outside shell of the battery. So what you end up doing is you end up having one piece of metal being the outside portion of it, and the other one goes like literally through the middle of it as like a core. And that's why this side here is positive, and this side right here is negative. There's always two parts. Oh, I wish that thing was working. I feel so disappointed right now. Okay, what I've got here are 4 definitions that I need you guys to know about batteries. I'm going to explain them for you right now, but I need you to look them up in your book too as well. The 4 terms are dry cell, wet cell, primary cell, secondary cell. It's actually right on your assignment, so you can actually answer this on your assignment right now as I'm talking. They kind of come in pairs. A wet cell, I'm going to start there, literally is wet. Just like the battery I made there that's not working yet, it's called a wet cell because you've got literally like liquid electrolytes. Okay, that's why it is a wet cell. However, I gotta be honest, most batteries, if you made them out of something liquid, it's gonna slosh around, it's gonna spill, it's gonna evaporate. That doesn't really make a lot of sense. So most of the batteries we work with are actually considered dry cells. And the reason why is that the electrolyte is like a paste. Have you ever seen like what happens when a battery is finally dead? You get that like kind of like white oozy stuff kind of around the edges of it. Have you seen that before? That's actually the electrolytic solution. That's the electrolyte. That's finally like oozing out of the side of the battery, which was like a paste. So if it's a battery that's made of just liquid chemicals like that one there, it's a wet cell. But pretty much all other batteries are dry cells because they don't actually use like liquids, they use a paste instead. So that's 2 types of batteries. The other types of batteries I need you to know are primary versus secondary. A primary cell is the kind of battery that once it dies, once it stops running anymore, the reason why it dies is that a connection is broken somewhere. This battery right here right now that I tried to make for the clock is not working. And somewhere along the way, there's a break in the circuit. I gotta try to figure out where the break is to fix it, but I'll work on that later. But as soon as the circuit gets broken, the battery dies and it stops. That's a primary cell. Most of the batteries we work with, once they die, we throw them away. A secondary cell then is a rechargeable battery. Your cell phones, for example, are filled with secondary cells. Because as soon as your cell phone dies, do you throw your cell phone in the garbage and get a new one? Yeah. No, what you end up doing is you end up recharging your battery instead. I took my microphone off. Hey, see, I like that microphone. Not around my neck. Won't be able to hear this video anymore. Oh, shit. Garbage. Okay. Now you can hear me if you watch the video again. So, dry cell involves a paste as the electrolyte. Wet cell involves liquids, just like the battery I tried to make there as the electrolyte. Primary cells, once they die, they're done. And secondary cells can be recharged. Okay. So now we've actually got 2 different ways of making electricity. Option 1, you generate it using electromagnetic induction, which means you have to move a magnet and a wire next to each other, which means you need a turbine. You need to use like wind or or tides or a hydroelectric dam to do it. Or the other option is you use batteries. And you use batteries to make yourself electricity. Both of those are valid options for making electricity. And because of that, we have a lot of cool devices we can make. One of the things I need to show you then is the two different types of current. You've probably heard the term AC/DC before. There's actually a band who named themselves after this. AC/DC, Back in Black, Thunderstruck. Yeah, TNT. Nice. Okay. You know the song. There you go. So AC/DC, they named themselves after alternating current and direct current. Two different ways of electricity being formed. I want to show you this in a picture here. This one right here is a little bit easier to see. This is direct current. Batteries give us direct current. Because what ends up happening is a battery puts electrons through a loop. They go through the light bulb, and they come back, and they just keep going over and over and over. And they just keep going in a loop over and over and over again. And as long as the loop doesn't get broken, like that one right there that's not working for some reason, as long as there's no break in the circuit, direct current keeps going in circles. Batteries do that. However, when we generate electricity using electromagnetic induction, almost always it's called alternating current. And it took a while for people to figure out why the current was alternating. I've got a picture here to kind of illustrate the idea. If you guys can see this animation I have right here, imagine that this is the turbine that like gets spun around by the dam or by the windmill or something like that. But something is spinning. Okay, this is the thing that's spinning right here. Watch what happens as it spins. Right here, it's going to push, causes the water to go this way. See, when it pushes, it goes this way. But then on the way back, it pulls, and the water goes this way. Then it pushes. Then it pulls, pushes. Pulls, pushes. Does that make sense? Because of that, that's called alternating current. And that's actually how the electricity in, like, say, our houses, it's actually alternating current that we get when we use, like, a regular outlet here. Because what happens is as the generator spins around in circles, something like this is happening, where the electrons get pushed this way, then pulled that way, then pushed this way, then pulled that way, then pushed this way. And so it actually goes like this. But it doesn't actually do like a full loop. In this example right here, it goes all the way around like this for forever. So batteries are direct current, whereas anything that's been generated using electromagnetic induction has AC current. It goes this way for a while, then it goes this way for a while. It goes this way for a while. But like it still is electricity, though. It still works. I can actually explain that to you a little bit using one of my first slides here. On one of the very, very first slides, this was Michael Faraday's experiment back in 1831. When he pushed the magnet in, it caused the electrons to spin one way through the wire. Now, when he left the magnet inside the bar, though, remember how it did nothing? But then when he pulled it back out, it caused electricity again? What ends up happening is when you push the magnet in, the electrons spin one way. And when you pull the magnet out, the electrons spin the other way. So as the magnet kind of gets moved, electrons go this way, then this way, then this way, then this way. So that's alternating current. So a very simple question I could ask you is, where would you find direct current? A battery. Only we wouldn't call it a battery, we would call it a cell. Yeah. And then if I ask you where do you find alternating current, you get alternating current because you have a alternating current comes from electromagnetic induction. And it goes back and forth and back and forth. Does this kind of picture help illustrate that idea to you fairly well? Okay, well, now that we've talked about how to make electricity, because like I said, I had two goals today. One goal was to teach you where we get our electricity from. Right? Hopefully now you know it's not just some magical pixie fairy dust land that gives us electricity. We either make it using a battery, that would be cool, or we have to generate it using some sort of generator. But once we have our electricity, there are many things we can do with it. And this is, again, just a basic concept of a circuit. In order for us to work, it has to be a closed circuit. It has to be a full loop. Okay? There's always three things required to make a circuit at the very least. You have to have a conductor, something for the electricity flow to go through. Usually that's wires. Okay. Second thing you need to have is an energy source, something that gives us the electricity. Could be a generator, could be a battery, I don't really care what it is, but something has to give us the electricity. But the third part, probably the most important part, the word is called a load. The load is something that you do with it, like a radio, or a microwave, or a cell phone, or a flashlight, right? Like you have to actually do something with the electricity. What I want to do on my last slides right here is show you some of the cool things that scientists and engineers have been able to create with electricity. So the first one's called an electromagnet. I'm going to show you one of these tomorrow in our lab. Anybody ever seen Toy Story 3? My daughters were watching it yesterday. At some point, there's a big electromagnet that causes all the metal to get like lifted up. Like a car crusher would have an electromagnet. Yeah, right at the end of the movie. It's so sad. Anyways, if you know what an electromagnet is, it's one of these sorts of things where oh, why is this getting stuck so much? It's one of these things where there's like this big magnet that can pick up like a huge piece of metal like a car. Yeah, it does. Okay, the way an electromagnet works is it's actually the exact opposite principle of electromagnetic induction. In electromagnetic induction, what you do is you take a magnet and you use the magnet to give you electricity. But the way an electromagnet works is you take electricity and it makes you a magnet. So what's really happening here is you have a magnet that you can turn on and off. Here's a basic picture of one, and I'll show you one tomorrow in our lab. You take a basic piece of metal like this right here, and you wrap a whole bunch of coils of wire around it. Then you attach it to a battery. I actually have one that I made that will actually, it wouldn't pick up a car, but it picks up other stuff. Yeah. And what ends up happening is you can make yourself a magnet that you can turn on and off. If you disconnect the wires and turn it off, the magnet stops working. But if you run electricity from a battery through all these wires here and put like a piece of metal through the middle, you can make what's called an electromagnet. So again, I'm just going to talk about these today. I'll show you them tomorrow in a lab. I'll just do it all in one day. So that's one cool thing you can do. You can make an electromagnet. Okay. Another thing we can do is also kind of the opposite. When Michael Faraday discovered electromagnetic induction, the idea was if you take mechanical energy, you take motion, you can make yourself electricity. Motion makes electricity. Well, eventually someone discovered how to make a motor. And the way a motor works is it takes electricity and creates motion. Probably the best example of this would be when Henry Ford discovered how to use a motor to drive a car. Right? And so what we can do is we can take electricity and use it to create motion instead. And it uses very much the same concept. It uses a magnet again and a coil of wire. And I want to kind of stand at the front here and try to explain how this works. Okay? Here's what you do. You take your coil of wire and you put it inside a magnetic field, but then you hook it up to a battery. So this right here implies there's a battery. Okay? Now what's supposed to happen here is that as the electricity runs through the wire, it actually causes it to start to rotate. Rather than motion causing electricity, you can actually have electricity cause motion. And again, I'll show you this tomorrow in our lab. What ends up happening is this side of the wire is actually going to start moving up. And this side of the wire right here is going to start moving down. And what ends up happening is it starts to rotate. The problem is that once it starts to rotate, it's just going to rotate 90 degrees and it would just sit like this. So your wire would have been like flat like this, and this side gets pushed up. This side gets pushed down, and so it rotates like this. The problem is that's not enough, because that's not a motor. A motor's got to keep spinning around in circles. So all motors have to have this thing. It's called a split commutator. See, there's like a little gap right down the middle here. What this does is it turns the electricity off just for a second. As soon as it gets perfectly horizontal, what happens is the electricity isn't able to conduct for a second. And so it's supposed to rotate to here, and then normally it would stop. But then you turn the electricity off. And what happens is its momentum keeps it rotating a little bit more, and then it can keep rotating. And what ends up happening is it causes it to go in a complete circle. And this guy right here more or less shows us that same thing. I'll show you closer, like one-on-one a little bit later. But if you guys can see here, see how there's like this little gap right down the middle right here where there isn't metal there? Come look later if you can't see. Like here there's metal all the way around. But like right down the middle here, there's actually a gap. That's called the split ring commutator. And it allows the thing to keep cycling in circles. So you have to have 3 pieces inside a motor for it to work. Here's the words I want you to know. One of them is called the armature. By the way, if I can give you some advice, this is on your test. A lot of the first group didn't do this very well. I think they missed paying attention during this part. So just so you know, this is on your test. The armature is the official word we give to the curved wire that spins in circles. If I were to show you this motor right here again, the armature then is this guy right here. See how there's like the spinny piece right here that's got all these wires right here? That's an armature. In this guy right here, this thing right here is an armature. It's going to start spinning. Okay. The word we give to the magnets that we need is called stator. Okay. You always have to have some magnets for this to work. It's electromagnetic, right? So we call that a stator. The last thing you need is that commutator, that little gap in the middle. Now, a lot of kids, even myself, I sometimes struggle with why do you need to have that little split commutator? And I've got an analogy here on this slide right here to kind of explain what the commutator is for, because a lot of kids, they don't get it. Okay. You guys are starting to learn how to drive, right? You're getting your learners in the next little while, or maybe you have them. Okay, well, so imagine that I want you to take a steering wheel. I'll stand this way, and I want you to start rotating it around in circles. Okay, imagine that my hands are right here, and then I want to start rotating the wheel. So I start turning, and I get to about there. I can't rotate it anymore because I'm running out of room. So what you really have to do is you have to turn the wheel. You then have to like let go, re-grab the wheel, and turn it some more. Well, I get what you're saying, but that basic concept though is that like you cannot keep rotating the wheel because you can't turn your hands around. That same problem happens in a motor. Okay, you can't keep spinning the motor around in circles because eventually what happens is it kind of gets stuck. That's why there's that split in the middle. What the split in the middle does is it turns off the electricity for just a millisecond. That's all it takes. In the same way as when I'm trying to turn the wheel, my hands are on the wheel, my hands are on the wheel, my hands are on the wheel. I take my hands off the wheel and start again. Take my hands off the wheel and start again. Does that make sense? I mean, I know that's not actually how you drive. No, because you actually you do two hands, but I get what you're saying. But do you guys get the whole point about how you can't turn a wheel by keep rotating your hands, at least in a full circle? That's what the commutator is for. So you can't do a full rotation without releasing your hands. Your hands have to come off the wheel at some point. At least one hand does. That same thing happens in a motor. That's why you have to have that split down the middle. So what the split down the middle does, guys, focus. It temporarily turns off the electricity. It breaks the circuit just for a second. In the same way that in order to turn a steering wheel, you have to lift your hands off the wheel in order to keep rotating it in circles. You know what I'm saying? So here's the slide I skipped then. This is another picture of a basic motor. Okay. 3 parts to the motor. You have to have a stator. You have to have magnets. You have to have a ring of wire. We call that an armature. And you have to have a split ring commutator so that you can actually keep it rotating in circles. Otherwise, it would get stuck. Okay. If this picture is starting to make sense, what ends up happening is if you run electricity through it, the electricity runs through the hot wire, through here, all the way around, and back through here, and through there. The electricity has a full circuit to go through. What ends up happening, and I'll show you this tomorrow in our lab just so you can kind of visualize it, is this side of the wire is going to get pushed down, and this side of the wire is going to get pulled up. And what ends up happening is it starts rotating, just like when you turn your hands on the steering wheel like this. The problem is that it's going to get stuck at some point. Hence, see how this guy right here, there's kind of like a gap. Can you see that gap, like right about there? As soon as it gets to about this spot right here, there's a gap. It turns the electricity off. It keeps rotating just a little bit more, and then it re-picks it up. And so that's the whole, lift your hands and keep rotating. Maybe not a steering wheel, but imagine that you had to like turn some sort of big like water valve kind of pipe, right? You have to like let go in order to like get your re-grip. That's what this thing here does. So there's another really cool device, and honestly, we use motors in a lot of the things we use, right? Cars, for example. A refrigerator has some sort of motor or compressor inside of it. Wait, let's move on here. Another device I need you guys to know about is called a transformer. Okay. If you guys recall, we talked yesterday about current and voltage. Okay. Well, yeah, not the movie. That's Transformers. I just want to talk about a transformer. Yeah, Optimus Prime, of course. Who else would it be? Although Bumblebee's pretty cool. Yeah. Okay. Anyways, do you guys remember what voltage is? How would you define voltage? how much energy it has. Yeah, if I were to drop 7 pens, that's like my current. If I drop 1 pen, I'm dropping less. But the energy I give it is voltage. Now, here's the reason why this matters. If I were to try to give a push to my electrons, and they had to go all the way from those windmills way over there to your house, that's a long ways to go. Does that make sense? Well, no, I mean, in the grand scheme of things, it is, though. Well, maybe unless you live there. But like for the windmill to send all of the electricity from there to our school, it's a long ways to go, which means it needs to have a lot of voltage. It has to get a really good push, because if you give it just a little push, it's not going to make it all the way here. So you need to have high voltage wires. In fact, I actually wrote it on here. High voltage wires is 500,000 volts in those overhead power lines, which makes sense because you got to push the electricity a long way. Here's the problem, though. Once that electricity gets to your house, we don't want it to be 500,000 volts. It's way too much. Does anybody know what the standard voltage inside a house is? It's usually either 120 for some devices or 220, 240, like a washing machine or like a range, like an oven. Sometimes those use like the bigger plugins. That's usually 220, 240. But most everyday plugins is about 120 volts. So we need to find a way to drop the voltage from huge voltage to push it to your house to something a little more reasonable. Because if you have way too much voltage in your house, it's going to cause problems there too. So hence the term transformer. And I actually had a picture of some transformers earlier in our notes. But here's like a basic idea of a transformer. You're going to want to like write down what I say here, okay? Because I don't actually have any words on this slide. Here's how a transformer works. There's one of two kinds. There's either the step-up transformer or the step-down transformer. This one right here is a step-down transformer. Here's how it works. You see how there's like 1, 2, 3, 4, 5, 6, 7, 8, like 9 curls on this side right here? But then on the other side of the little iron ring right here, there's only 3 coils. This is basically how a transformer works. You hook up some voltage to this side right here with 9 curls, and then on this side over here, you only hook up 3 curls. What ends up happening is you might have started with 100 volts over here, and then on this side right over here, you'd only have 20 volts, because it's going to step the voltage down because there were more coils to less coils. Does that make sense? It reduces voltage for you. Okay. So there are transformer boxes found around town. Sometimes they're on the power lines themselves. Sometimes there's those like big green boxes outside of someone's house. Seen one of those? Sometimes in those things you have a transformer, and it takes the electricity from being 50,000 volts and drops it down to like 120. Or you might need a step-up transformer. A step-up transformer is just the opposite. So this one's step up. Step up. You're going to start with a few coils. Like say you start with 10 volts right here. When you're done, because there's more loops over here, this is going to give you, say, 50 volts. Right? You're going to start low and get higher because you go from less loops to more loops. Okay, that's what a transformer does. It changes your voltage. Does it change your current? What is current again? Yeah, current is how many electrons are moving. Voltage is how much of a push we're giving them. So what really ends up happening here is right here we're slowing them down. We're giving them a less of a push by changing the amount of coils you have. Oh, this thing doesn't want to slide anymore. You used to have 9 coils here, then 3 coils here. You're kind of slowing them down basically. But you still might have the same number of electrons moving. They're just moving at a slower speed. Why are they moving at a slower speed? Well, there's less wire. There's less like loops going on here. No, that's a transformer. Okay, the last thing I need to teach you guys about is something called electroplating. Basically, the idea behind electroplating is that you coat the outside surface of a metal with a different metal. And so only the outside is like the special metal. Like, say, gold-plated something. Ever heard of like gold-plated silverware or chromium-plated stuff on trucks is actually really big. Have you ever had like the chrome package on a new vehicle? What you end up doing if you get like gold-plated or chrome-plated is that the inside is a cheap metal, like lead or tin or zinc or something, and only the very outside is gold. Usually it's gold or silver. Those are the two most common because they're precious metals. or sometimes we use chrome, like say on this tire right here. Here's how this works. I got to show you the basic premise. Yeah, I got time here. What you're going to do is you're going to take a battery, and the battery is part of the electro part of this, right? It's called electroplating. What you're going to do is you're going to take electrons and you're going to run them through a circuit through this battery. And what's going to happen is there's going to be a whole bunch of electrons on this piece of metal right here. Well, then you dip it into some sort of solution, and what happens is ions are going to become attracted to this piece of metal right here, and in doing so, it coats the outside of it, just the outside, with a new metal. So like the inside, it's kind of like those Cadbury eggs. You guys ever eat those at Easter time? The inside is the cream filling, but the outside's covered in chocolate. Same thing right here. The inside is still lead, but the outside is gold. If you were to scratch it, you would notice that like as soon as you scratch the top layer off, it's actually cheap on the inside. I got better pictures here to help show the idea. Here's a different one here. What's supposed to happen here is you run your electricity from here to here. So the electrons are going to run from one side to the other. And in this picture here, the electrons are these little red dots. See those red dots there? The electrons are going to come from here through here. So you're going to have extra red dots sitting over here. Now what ends up happening is this piece of metal right here, it's going to lose its electrons, but it's also going to spit off some ions. See how these guys right here are missing like an open spot here where the red dot would have been? It's because the electron goes this way here. Well, these guys then reattach over on the other side right here, but they attach on the outer surface. So like this object here is pink on the inside, but orange on the outside. We call that electroplating. And we actually do that on a lot of things. For example, like this faucet right here is probably electroplated. I bet you it's probably copper or zinc on the inside, and the outside is chromium. So it looks nice and shiny, but like rather than all of it being chromium, only the outside of it is. Does that make sense? The most common places you see this would be in like these pictures here, like the rims you have here. They're probably iron rims with chrome on the outside, so they look really special. Okay? Or this silverware right here. It's probably not pure gold. It's probably made of something else, and gold is on the outside. Okay, let me do a quick summary, and then you guys have just a few minutes left here to probably work on, I'd say, that assignment. Hopefully we covered 2 main topics today. Actually, let's make it 3. First thing I taught you about is you have to know where electricity comes from, okay? It doesn't just magically show up. There's 2 main ways we get electricity. One is a battery, okay? I'm going to make this battery work, I promise. I will eventually make this work, so just give me some time. The way a battery works is that electrons basically run through a wire from electrode to electrode. They always run from anode to cathode, which is the negative and positive sides of a battery. And if you have a full and complete loop, you can make electricity. Here's a big problem, though. What happens to batteries? They eventually die. Yeah, and this one right here is basically a dead battery because somewhere in here I have a broken loop. So I'll fix it. The more common way that we make electricity, though, is through a generator. You use a turbine. And this is all based on Faraday's discovery back in 1831. You take a magnet, you take a coil of wire, and you move them. You can make electricity. And I'm going to show you this tomorrow in our lab. Okay? I'm not going to be able to generate enough electricity to like light something up, but I'll make enough that we can notice it at least. Okay? Because of that, we can do a lot of cool things with it. Now, I mean, from cell phones to cars to lights, there's a lot of things we can do, but there are a few main things that I need you guys to know because it might be on your PAT. So that was things like how we can use electricity to electroplate, how a transformer works, how an electromagnet works, how a motor works. Some of those like common things that we make using electricity, I need you to know the basics of those. Okay, so those are the 3 things. Do you know how a battery works? It uses direct current. Do you know how a generator works and how it uses alternating current? And do you know a few of the things that we do with it? Okay, so I'm now done. I've now actually taught you guys 3 out of 5 lessons. We're actually more than halfway done our unit, believe it or not. Yeah. Was that? Okay, so watch the video on the 3rd one, okay? So here's my suggestion, guys. I know there's only 10 minutes left. Use that 10 minutes. Work a little bit on your assignment on some of the questions we haven't done. Tomorrow we're going to do a lab. Friday we have no school. I believe Monday was a work day, and then Tuesday we're going to try a quiz. The advice I would give, try to finish the assignment before the quiz, because that's your studying for it. Okay? Mark it yourself. and then ask me to help with anything you didn't get. Fair enough? Okay, I'll stop talking. You guys have 10 minutes. Do what you need to with it, okay? I'm going to make this clock work eventually.